My name is Melissa Connelly. I'm a geologist at Casper College, and I have spent many years looking at the Morrison Formation in Wyoming. My main interest or focus is paleoecology, so I'm looking at the where animals lived and with whom and that type of stuff.
And how does geology help you?
Well, besides just looking at the individual animals and finding out who's living there, we need to know what the environment was like. And so geology, understanding the rocks around the animals, can give us an idea of what those environmental settings are. Ralph's site is really interesting. We're still working on the details, but what we've noticed is a couple things. First, we've noticed that the specimen, Ralph, the bones had been deposited on top of what appears to be an overbank deposit, or off the edges of a river system, in which you would get soils and lots of plant life living in those regions. And shortly after Ralph's death, a flood of some sort came in and deposited other materials on top of and preserving the bones, protecting and preserving the bones. And we see that it was probably a little back swamp or a little oxbow lake-like environment for a short period of time. We can tell that from the rocks here. This layer down here, this green blocky layer, this is a mudstone, and it's very blocky. Instead of a finely laminate, it's real chunky, and that tells us that these sediments, once it was laid down, were churned up through soil processes, plants and insects and worms and things like that, churned it up, and so it's not laminated anymore. And this tells us that we have this overbank or floodplain. But the material, and this is what Ralph was sitting on top of, but the material that encased Ralph is this darker brown material here. And it's a little coarser, and it also contains a lot of plant fragments, a lot of wood, coal that's been turned to coal. And this is something that you would expect to see in a oxbow pond or a little back swamp associated with a river. So the actual flow, there was a flow for a short period of time, and then it filled in with water, and over several years, sediments would fill in and the pond would dry up, and preserving those bones.
What's the oxbow term?
Oxbow, it's a term that describes a channel, a river channel that meanders. So as a river is meandering back and forth, sometimes the bend of that meander gets cut off, and the river will change its direction. And something like the Mississippi has meanders, and you'll notice a lot of ponds or lakes or old parts of the Mississippi that used to flow in those regions. Well, once it gets cut off, there's no influent water going into those regions, and they just turn into little ponds and lakes, and slowly will fill up with sediments. And we call those oxbow ponds or oxbow lakes.
Is that something that happens in a mature river system?
Yeah, it's a river system where the river isn't eroding. Okay, it's just carrying sediments and slowly depositing these sediments. So it's not like your stream that you would see in the mountains with waterfalls or anything like that. These are slow streams and very quiet or slow meandering rivers that you would expect to see on the plains or maybe even near the delta, like in Louisiana, or even all the way up through to the Missouri River, those areas.
So, are there is there a set criteria or some kind of checklist that you look at when you're analyzing a place? What kind of things do you look for, I guess?
Oh, we look for almost anything that's different or unusual. We look at the rock type first. We call that lithology when we look at the rock type. Is it made out of clay, or is it made out of sand? Is it conglomerate? Does it have big chunks of rock into it? And then we look at the geometry of those rocks. Are they thick, widespread sequences, or are they very thin and laminar sequences, or do they come and then disappear over a short period of time? So that's the geometry of those beds. And then we look at the mineralogy. What is it made out of? If it's the sandstones, are the sandstones made out of quartz, or are they made out of feldspars? And it gives us an idea of the source of these sediments and where they came from. Mineralogy in the clays can help us interpret environments. Illite clays are often associated with soils. If you have clays that's rich in what we call smectite, or an expanding clay, kind of like kitty litter, okay, that expanding clay, that mentions or kind of tells us that there may have been some sort of volcanic influence in the region, volcanic ash dumping this clay into the river systems. And those are actually really useful because we can sometimes use that type of clay for dating the rocks, so we can get a really good idea of how old those rocks are.
Is there any evidence of volcanic remains?
Not a whole lot. It's pretty quiet. We are collecting samples, and we're going to try and see if we can find some expanding clays. But it kind of looks pretty like you're very far away from the volcanic source. So if there is some, it's not enough to say that the volcano was nearby. It was quite a ways away.
Any conclusions from this site?
Well, we've collected a lot of data. We've taken some measurements. The hardest thing that we're working with is the Morrison in Montana is not very well known. There's a few papers out. So what we're trying to do is compare this site to the classic locality, and there's a lot of differences. So it's going to be a little bit challenging. It's kind of like the Morrison here in Montana is the abridged version of the Morrison Formation in the classic regions of Colorado and other Rocky Mountain states. So we're challenged into trying to figure out exactly where we are in the section, what the timing, what the period is. Are you at the end of the Morrison, the beginning of the Morrison, or do you have the whole Morrison here and just really compact and really shortened? So there's a little hints here and there of what's going on. So we're still working on that. And we're going to try and do a lot of literature search. We're going to see what others have done in the region, compare the mineralogy, the samples that we've collected, see if we can find some matches and give us a really good idea of what's going on.
How many states does the Morrison come from?
Just about all the Rocky Mountain states, Montana, Wyoming, Colorado, New Mexico, Utah, and I'm sure Arizona and maybe Idaho has a little bit. But it's basically all the Rocky Mountain regions. It was an area or a time period where there was a seaway that would come into the middle of the United States, and then it would leave, and it would come in, and it would leave, and it did this back and forth during the Jurassic and the Cretaceous several times. And the Morrison was one of those times when the sea was retreating, and all of the terrestrial sediments were filling in that retreating seaway, and at the end of the Jurassic. And it just happened to be the time when we have the wonderful dinosaurs, the big giant sauropods like Ralph, and stegosaurs and allosaurs, and the real Jurassic Park, you might say. So but this is new. This is all new to us, and we're all running around scratching our heads trying to figure out. I'm sure there's going to be lots of arguments about this over the years. The Morrison people are very serious about their formation, and so it'll be an entertaining event for a long time.
What kind of thickness does it have?
You know, it appears pretty thin here. In some places it's 250 feet or more. It can be very thick. Utah has some of the thickest sequences. Here it just looks kind of small, like 50 to 100 feet maybe. You know, it doesn't look like it's very thick. We have two good sites that we've been looking at, and I think we can tie them together. The vegetation out here is kind of hindering things a little bit, but you can't see the soils, yeah. So we're running around looking at every outcrop we can find and see if we can't tie things together. And I think we will. It'll just take us some time to look at the data and redo everything.
And earlier I heard you refer to upper and lower. Does that have to do with the age of the?
No, it doesn't. Formations are based off of many things, but one of the things that defines a formation is the lithology. What are the rocks? What is it made out of? And you also have to be able to map a formation. You got to find the contacts and be able to walk them out. So there's several criteria for formation. Time has nothing to do with it. Although we often put time in to try and use it as a boundary, but it's the lithology that's more important. So when we talk about the upper and lower, the Morrison formation can be divided into members, into smaller packages that are recognizable. And in some areas there are 6 members to the Morrison. In Wyoming it was just recently divided into 2 members. And up here I don't believe it's divided at all. So when we say upper and lower, there's these classic events that happen during the Morrison that are represented in the rocks. The early part of the Morrison, the lower part, is often described as an event where the sea just retreated and we have these low-lying swampy areas. We get ponds, then we get the rivers, and then we get the paleosols or the soils, the red and green mottled stuff, and lots of sand. And then later on, about halfway through the Morrison time period, volcanic activity increased. And so these volcanoes back in, I don't know, Nevada or someplace way west is dumping all this ash material into the sediments, and it's choking up the ponds, and the fauna changes, and the environment's changing a little bit, and it becomes more humid. And that's why we're finding the coaly swamps and slightly different clays in the soils. And so there's the classic change from lower to upper Morrison. So we're trying to find that change here, and I think we can see it. But like I said, it's kind of a bridge, and it's really condensed, so finding that exact break might be difficult.
Do they ever just drill test holes down to get core samples and try to find those strata?
They do, usually if they're looking for oil or petroleums, but to drill a core for a paleontological research project is awfully expensive. So, but what we can do is we can go back to those old logs from the when they drilled the wells in the region, and we can look at those old logs, and we can at least map the thickness of those formations, and we can see what it's trending, what the trend is coming northward. And that's one of the things that we will be looking at, is some of the older what we call electric logs, or tests that they do down the hole. Now, finding a core through the Morrison probably is not going to be easy to do, but I'm sure we can find the data anyway. The data should be described somewhere. And the Oil and Gas Commission is a great place to find that kind of stuff. So.
Yeah, they've been drilling everywhere.
Yeah. Well, they actually just kind of store the data. The rigs and everybody else, they do all the drilling, but the Oil and Gas Commission tends to handle the permits, and there's a warehouse basically for data. That's kind of an exchange.
So that's one of the tools you use?
Yeah, yeah, we can use that. Helps us with gross lithology. We can't look at individual beds, but we can say, oh, Morrison's 50 feet thick and 30% of it's sand, or something like that. We can do that.
And how long have you been doing it?
I've been working in the Morrison Formation for, let's see here, since '94, so 12 years now. Surprisingly enough, just on a personal note, I lived in Morrison, Colorado. So when I was a little kid, you know, at the age where the impressionable age, you might say, and so on a field trip in school, we went to see one of the first dinosaur pets with Brontosaurus, you know, and I was hooked ever since then. So who would think I'd be digging dinosaurs in the Morrison Formation as an adult, but I sure love it.
And what led you to geology?
Well, as a geologist, I can not only work with fossils, but I can also help understand the environments. And as I mentioned before, I really enjoy looking at paleoecology. So to do that, I got to know what the environment's like, and to know the environments, I got to know the rocks. And I love geology. And when I'm not digging, I'm a an instructor at Casper College, and I teach geology for geology students, but also for teachers and others who are interested in the field. And I just find that probably the best job in the world. And living in the Rocky Mountain region, I mean, we got geology all around us, so can't get any better than this.
Yeah. Wow. What do you think is the significance of this kind of study?
Well, oh goodness, there's several realms. I mean, we can do this for everything you can think of. Looking at ecology helps us understand our own ecology of today, even though we have different animals. But the niches are the same, and the web of life is the same. You just replace the individuals. But oh gosh, there's just so many reasons. There's you can, as a scientist, of course, it's just trying to learn, all that's around you, appreciate the world around you much more. Dinosaurs is great. Adults love dinosaurs as much as kids do, so don't let your parents tell you otherwise. We do love dinosaurs. And it opens the world to other things. It opens the world to imagination. You can think about math with dinosaurs. You can think about the astronomy with dinosaurs. It's just a whole world that you can use your imagination for, and it's real. This is real. This was real here, and it's 150 million years old, and it just boggles the mind. But it's just a wonderful way of being a kid again for us adults, or if you are a kid, to use that imagination and go with it. And you can use this in any field, anywhere.
So do you look, when you're trying to do the ecology, are you looking at the flora too?
Oh yeah, everything.
Are there traces of the flora in the...
Yes, there are. In this layer right here, there's lots of, sometimes we find little black blebs of coal. And the coal is plant material, and we find little leaf impressions and things. I'm not quite sure exactly what they all are, but some of it appears to be from cycads, cycad material, and ferns. Which is very common in the Jurassic. Now remember, in the Jurassic we didn't have flowering plants much, although some people are arguing that, but most of us still agree that there weren't flowering plants in the Jurassic. So it helps us understand what the environment was like. Was it swampy, or was it a forest, or was it open savanna-like material? So the plants are very, very useful. The pollens, if we looked at pollen, if we could collect pollens, that can also help us identify the plant life that's around us, or at this time. Pollens can also be used to help date the site, because certain plants lived at certain time periods. So that's also very useful.
I'm sorry, there's pollen records in the geology, in the rocks?
Yes, yeah, there's lots of palentologists look at pollen, and it's a microscopic thing, so it's not something I can do. We would have to send it off to an expert. But yeah, you can look at pollens, and it can tell you what kind of plant communities was around at that time, and that can be very helpful in understanding ecology.
So is that in the form of trace minerals, or do you actually find pollen in the...
Well, it's been replaced, but it's been replaced on such a molecular scale that you can still see the surface texture and the shape of the pollen grain, and so we can look at those and compare them to known pollen families, and so we can tell whether it's a fern or a conifer, or if it's something like that.
And so that's heavy-duty microscope work?
Yeah, heavy-duty microscope work, yeah.
They slice those real thin slices off? And just mineral stuff?
It's a variety of techniques, yeah.
Can you explain what the cycad term is?
A cycads are cool. They're a plant that tends to have kind of a base, kind of like a palm-like plant. Has a base that looks kind of like a pineapple, and then it has these big palm fronds that come out from the center. And they can be very small or very, very large. They're very tough, and they live today. You can go to a greenhouse somewhere and find a cycad, and there's such a huge variety. And when you do, if you do that, touch the leaves and feel the leaves, and you feel how stiff and hard they are, and you think, I can't believe a dinosaur would eat this, but some think that they were probably a major food source for many of these guys.
Are they related to a pineapple?
No, I don't think so.
Appearance?
Yeah, just similar.
Are they like a succulent?
They're a tropical or subtropical plant, and you see them in Florida and in southern states. They grow everywhere.
Like a yucca? That's a different thing.
That's kind of a different thing, yeah.
So what do you think the environment was like here during that time?
Well, it looks like we're getting out of the freshwater, clean, alkaline, dry seasonal environment and start moving into an environment where we have the big rivers, but we also have quiet waters, and more stagnant waters, maybe a little bit more acidic waters. So I would suggest that we would have something like maybe a light forested area, low flow moving rivers that occasionally flooded, and it's sort of a subtropical, warm environment. I don't think it would freeze at night. But I'm trying to think of what would be a good example. The Morrison itself is often compared to the Okavango Delta in Africa. So that's always a good place to look when you're trying to comparing environments. But in North America here, I guess we could compare it closer to, let's say, Oklahoma or Louisiana, not as far down to the coast, but low flat-lying area with probably lots of trees.
What I was just wondering about the magnetic pole shifts that have happened.
Mm-hmm.
Are they? Is the last one before, during, after the Jurassic?
They've happened often since then. Okay, so it's constantly flipping back and forth. Very short period of time if you're talking geologically. I think maybe 10, 60,000 years or so, there's a minor shift, a flip. And so yeah, it happens a lot. And
didn't affect anything to do with dinosaurs, really?
No, it wouldn't bother us. If it did, I mean, there would be an extinction every so many thousand years,
Would that affect the climate much?
No, I don't think it would bother the climate much at all. It's just a magnetic field. What it could do, though, see, the magnetic field encompasses the Earth on the outside of the Earth, and it deflects the solar winds that comes off of the sun as it comes towards the Earth. This field blocks it and sheds it and protects our atmosphere. If we didn't have a magnetic field, we would all fry. I mean, with UV radiation and other gamma radiation and stuff, bombardment from the sun. So it's very, very important for us. If it weakens, it is, I guess, possible that those radiation levels could increase. But as far as I know, there's not much evidence suggesting that there was large-scale influence caused by this magnetic shifting.
According to the record of how often the shifts, we're kind of overdue, aren't we?
Yeah, it's supposed to shift soon. Yeah. I don't know if it'll do it in our lifetime, but so we just paint the other side of the needle on our compass,
Cell phone.
Yeah.
So, do you have any advice for any young people that might be interested in getting into this?
Yeah, if you like dinosaurs or paleontology or geology or archaeology, I would suggest contacting your nearest museum and just get involved, volunteer. Visit the museum, read up on it, but volunteer. If they take volunteers, you might do grunt work for a while, but that's how I got started. I volunteered at a museum, and they just loved our help, and it just blossomed into a whole career. So if you like this, get involved with your nearest museum, support them, with helping out, volunteering, even financial support. Museums around the country needs your help, and I really would recommend you to do that.